Hello students, in this lecture pertaining to combustion in SI engine, today we will discuss the abnormal combustion and particularly the detonation and the design principles of combustion chamber for SI engines. So till now we have discussed the normal combustion in SI engines, and in normal combustion the flame front which was generated by the spark ignition that travels across the combustion chamber in somewhat even way, in somewhat normal way. Now there are certain engine operating conditions under which abnormal combustion may take place, which is not only dangerous to life but deteriorates the performance of engine. And there are various ways in which abnormal combustion can occur. It may be detonation or knock, or pre-ignition, or run-on. And out of these, detonation or knock is the most important because it basically puts restriction on the compression ratio at which engine can be operated, or you can say it controls the efficiency and to some extent power output. Now, in the figure on the slide, we are showing you how normal combustion or how the combustion with detonation is occurring. Now, in the normal combustion, basically the normal flame front, it is basically traveling across the combustion chamber from A to D, and the speed of the flame front is about 15 to 30 meter per second. Now, as the flame front is advancing, it is basically compressing the unburnt charge B''D, raising its temperature. Now the temperature is also increased by radiation from the advancing flame front and also due to the reaction taking place in the unburnt mixture itself. Now if this unburnt charge is not reaching its critical temperature for autoignition, it will not autoignite, and the flame front BB' will move across through the unburnt charge to the farthest point of the chamber D in the normal manner. The P theta diagram as shown on the slide for the normal combustion is going to be a smooth curve. Now in the abnormal combustion, which we also call detonation or knocking, the end charge autoignites before the flame front reaches it. Now in order to autoignite, the last unburnt portion of the charge must reach above a certain critical temperature, and this critical temperature depends upon the condition of pressure and density of the unburnt charge and remain at this temperature for a certain length of time. Now during this period, certain chemical reactions take place which prepare the charge for autoignition, and the time required in this preparation phase is called ignition delay. Now what is happening in abnormal combustion or the combustion with detonation? The flame front has reached BB' and the unburnt charge BB''D has reached the critical conditions for autoignition. Now in this case there is a possibility of detonation or knocking. If the flame front can proceed from BB' to D and consume the unburnt charge in a normal manner before the completion of delay period, there will be no detonation. But if the flame front is able to proceed only up to CC' during the ignition delay period, then remaining portion of the unburnt charge CC'(D) will autoignite and cause extreme pressure fluctuations as shown in the P theta diagram on the slide. Now in autoignition, the burning is almost instantaneous, which results in the extremely rapid release of energy, causing pressure of the end gas to rise almost 3 to 4 times from 50 bar to 150 bar. Now this large pressure variation gives rise to severe pressure wave which strikes the cylinder wall and sets a vibration, a characteristic high pitched metallic ringing sound as if somebody is striking it by light hammer, and this phenomena is known as knocking. Now it must be surprising that how a noise can be set up by pressure waves. So one can think logically in this way, that a noise of hammer blow is due to the vibration set up by the sudden and local high pressure produced under the hammer, and in the engine the local pressure is as high as 150 to 200 bar. Now from the description pertaining to the phenomena of detonation, it is clear that the commencement of detonation is very much dependent on the properties of the fuel, and if the unburnt charge does not reach its critical temperature, then there will be no detonation. Moreover, if the ignition delay period is longer than the time required for the flame front to burn through the unburnt charge, again there will be no detonation. Only when the critical temperature is reached and maintained, and the ignition delay is shorter than the time it takes for the flame front to burn through the unburnt charge, there will be detonation. So in order to avoid or eliminate detonation or suppress detonation, a high auto ignition temperature and a long ignition delay are desirable qualities for SI engine fuels. Now you can see in the diagram shown on the slide that in the normal combustion the P theta diagram is very smooth, but during the slight knock there are certain pressure fluctuations, and in the intense knock these fluctuations further amplify. Now the effects of detonation, noise and roughness. See, mild knock is not harmful, but if the intensity of knock increases beyond a certain limit, then a loud pulsating noise is produced due to the development of pressure wave, and this pressure wave vibrates back and forth across the cylinder, and that is basically again leading to the crankshaft vibration, so the engine run rough. Mechanical damage. In knocking, basically a local very rapid pressure rise is observed with subsequent waves of large amplitude. Now these waves of large amplitude along with the rapid rate of pressure rise is basically giving rise to increased rate of wear. Now detonation is very dangerous in engines having high noise level. In small engines the knocking noise is easily detected and the corrective measures may be taken, but in large high duty engines it is very difficult to detect knocking noise, and hence corrective measures cannot be taken. So if severe detonation persists for a long time, they may basically result in complete wreckage of the piston. Now detonation also results in increased carbon deposits. Increase in heat transfer. Knocking is basically accompanied by an increase in the rate of heat transfer to the combustion chamber walls. The increase in heat transfer is due to two reasons. The minor reason is that of the maximum temperature in the detonating engine is about 150 degrees Celsius higher than in non-detonating engine due to rapid completion of combustion. So basically the reason for the increased heat transfer is the scouring away of the protective layer of inactive stagnant gas on the cylinder walls due to pressure waves. This inactive layer of gas normally reduces the heat transfer by protecting the combustion chamber walls and piston crown from direct contact with flame. Now due to increase in the rate of heat transfer, the power output as well as efficiency of the detonating engine decreases. The increase in the rate of heat transfer to the walls of cylinder is also yielding to another effect. It may cause local overheating, especially of the sparking plug, which may reach a temperature high enough to ignite the charge before the initiation of a spark, thus causing pre-ignition. Basically, to prevent knock in the SI engine, the end gas should have a low temperature, a low density, a long ignition delay, a non-reactive composition. So the engine variables affecting detonation can be classified under 4 factors, namely the temperature factors, density factors, time factors, and composition factors. Now the temperature factors. Increasing the temperature of the unburnt mixture by any factor in the design or operation will basically increase the possibility of knock in SI engine, because all combustion reactions leading to lower delay periods and greater formation of chemical species are enhanced by increase in temperature loss. The temperature of the unburnt mixture is increased by following factors. Raising the compression ratio. Increasing the compression ratio increases both the temperature and pressure, that is density of the unburnt mixture. Increase in temperature reduces the delay period of the end gas. Increase in temperature as well as increase in pressure both basically lead to the greater collision of molecules, thus resulting in greater formation of chemical species responsible for knocking. Hence, the tendency to knock increases. Now, for a given engine setting and fuel, there will be a critical compression ratio above which knock occurs. This compression ratio is called highest useful compression ratio. Materials with high conductivity coefficients such as aluminum alloys are desirable for high compression cylinder heads, since a cool combustion chamber wall is essential for high compression without knock. However, hot spots may develop because of poor circulation of the coolant or improper distribution of the metal. Supercharging increases both temperature and density. Raising the inlet temperature, delay period decreases and velocity of flame travel increases. Raising the coolant temperature, delay period decreases. Increasing the load, that is opening the throttle, and increase in the load increases the temperature of the cylinder and combustion chamber walls, thereby raising mixture and end gas temperatures. Also, the pressure of charge is increased, hence the tendency to knock increases. Raising the temperature of the cylinder and combustion chamber walls. The temperature of the end gas depends on the design of combustion chamber. Spark plug and exhaust wall are the two hottest spots in the combustion chamber, and hence end gas should not be compressed against these. Advancing the spark timing. When the spark is advanced, burning gas is compressed by the rising piston, and therefore both temperatures and pressure, that is also densities, they are increased. Thus, tendency to knock increases with advanced spark timings and decreases with retarded sparking timings. By retarding the spark timings, the peak pressures are reached farther down on the power stroke and are thus of lower magnitude. If in a given engine the fuel quality is changed and knock takes place, retarding the ignition may eliminate the knock, but it will also reduce the engine power. Increasing the density of unburnt mixture will increase the possibility of knock in the engine. That could be done by increasing the compression ratio, by opening the throttle, that is increasing the load, by supercharging the engine, or by increasing the inlet pressure. Now the other three, above three, first, second and third, have been discussed previously. Now we will discuss the fourth one. Any increase in the inlet pressure basically increases the overall pressure during the cycle. The high pressure in the end gas decreases the delay period, which consequently increases the tendency of the charge to detonate. But an increase in the inlet pressure increases the flame velocity, which would reduce the tendency to detonate. But the first effect remains dominant. Therefore, with increased pressure, tendency to detonate always increases. Now the fifth, advancing the spark timing also increases the tendency to knock, that has been discussed previously. Increasing the time of exposure of the unburnt mixture to auto ignition conditions will increase the probability of knock in SI engines. Increasing flame travel distance, that could be done by incorporating changes in combustion chamber design, or by suitable positioning of the spark plug, or by incorporating variations in engine size. So the possibility of knock can be increased by increasing the flame travel distance, means the time taken by the flame to traverse the combustion chamber. That may be done by the suitable combustion chamber shape. Now this is thumb rule that more compact the combustion chamber, better will be its anti-knock characteristics, as the flame travel and combustion time will be shorter. Moreover, if the combustion chamber is highly turbulent, means its contents are in turbulence, the combustion rate is higher and consequently combustion time is further reduced. This further reduces the tendency to knock. Now, location of spark plug assumes a great significance. Spark plug, if located centrally in the combustion chamber, that will have minimum tendency to knock as the flame travel is minimum. The flame travel can be reduced by using 2 or more spark plugs. Now, one more important thing is the location of exhaust valve. The exhaust valve should be located close to the spark plug so that it does not lie in the end gas region. Otherwise, there will be tendency to knock. The delay period is not very much affected by the size of the cylinder. However, a flame requires a longer time to travel across the combustion chamber of a large engine. So the large engines have a greater tendency to knock as compared to that of smaller engines. That is why the SI engine are generally limited to 100 mm bore, means you won't find SI engines having size more than 100 mm. Now, decreasing the turbulence of the mixture basically decreases the flame speed and hence increases the tendency to knock. Now, turbulence depends basically on the design of combustion chamber and on an engine speed. Decrease in the engine speed decreases the turbulence of the mixture, resulting in reduced flame speed. Moreover, lower the engine speed, longer is the absolute time for flame to traverse the cylinder, which increases the time available for pre-flame reactions. Hence, the tendency to knock is increased at lower speeds. The properties of the fuel and the fuel-air ratio and the primary means of controlling knock once the compression ratio and engine dimension are selected. Now, octane rating of the fuel. The tendency of an engine to knock is very much affected by the properties of the fuel used. In general, you can say lower the self-ignition temperature of the fuel or greater its pre-flame reactivity, the greater is the tendency to knock. Octane number is basically a measure of resistance to knock. Higher the octane number, lesser will be the tendency to knock. Now, paraffin series have the maximum and aromatic series have minimum tendency to knock, whereas naphthalene comes in between the two. There is somewhat general relationship between molecular structure of the paraffins and the knocking tendency. Increasing the length of carbon chain increases the knocking tendency. Centralizing the carbon atoms decreases the knocking tendency. If you add methyl group to the side of carbon chain in the center or position, it also decreases the knocking tendency. So in aliphatic hydrocarbons, unsaturated compounds have lower knocking tendency than that of saturated hydrocarbons, with the exception of ethylene, acetylene and propylene. Now, if we compare naphthenes and aromatics, naphthenes have more knocking tendency than the aromatics. Lengthening in the case of side chain increases the knocking tendency, whereas branching of the side chain decreases the knocking tendency. Now, the most important effect of fuel-air ratio is on the ignition delay. When the mixture is nearly 10% richer than stoichiometric, ignition lag of the end gas is minimum. Now, this is one effect. The second phenomena or the second important thing is that of velocity of propagation, flame propagation is maximum when the mixture is 10% richer than the stoichiometric. But the former effect, that is minimum ignition lag effect, predominates and the knocking tendency is found to be maximum. And you should note that at this point the power is maximum. By making the mixture leaner or richer, the tendency to knock is decreased. A too rich mixture is especially effective in decreasing or eliminating the knock due to longer delay and lower temperature of the combustion. Now, humidity of air. Increasing atmospheric humidity decreases the tendency to knock, decreasing the reaction time. Incomplete combustion of fuel results in the deposit of ash on the walls of the combustion chamber, which later on enhanced by the dirt in the air and by unscavenged additive products. Now, the proportion of the combustion heat which normally flows through the chamber walls may be largely absorbed by these deposits and they are transferred back to the fresh charge. More, by reducing the clearance volume, the deposits increase the compression ratio. Now, with the given fuel, the tendency to knock will increase with time as the deposits build up and become increasingly effective. In other words, we can say the octane requirement of the engine increases. Now, as we have studied till now that efficiency of an engine can be increased by increasing the compression ratio. But we also know that the maximum compression ratio that can be used is limited by detonation. So from the viewpoint of the efficiency, the engines therefore can be designed such that detonation takes place at low engine speed and high manifold pressure, that is full throttle. So ignition is retarded, means ignition is taking place ahead of top dead center, say 20 to 10 degree before top dead center. So in order to prevent the detonation at high engine speeds and partly open throttle, means when car is running at constant speed, the automatic mechanism return the ignition timing to open timing. Now we have read the effect of engine variables on the detonation, and we can say that knocking can be controlled only by some of the manipulations like increasing engine RPM, retarding spark, reducing pressure in inlet manifold by throttling, making the ratio too lean or too rich, and it is preferred to make the mixture rich. This would basically reduce the efficiency, but power output will be maintained. If we make the mixture leaner, then that reduces the power output. Now water injection increases the delay period as well as room temperature. So injection of water can be up to 50% of the fuel. So we can say that these are basically some of the design features which reduces the knock. Use of lower compression ratio, increasing turbulence, relocating spark plugs or by the use of multiple spark plugs, by the suitable design of combustion chamber so as to reduce the flame length and the temperature of the end gas. Moreover, the use of high octane fuel can eliminate detonation. High octane fuels are obtained by adding additives which are known as dopes to petrol. Now question arises, can we detect the detonation? Because control measures can be taken only when detonation is detected. So following methods are the prevalent ones to detect detonation. Detonation may be heard if the engine noise is not too high. Now the temperature of the spark plug gasket can be measured by a thermocouple. High temperature means detonation is occurring. The vibration set up by detonation can be measured by knock meter having a vibrative electric pickup. Also the presence of intermittent puffs of grey smoke in exhaust, that also indicates that detonation is occurring. See, the design of combustion chamber has a great impact upon the engine performance and its knock properties. The design of combustion chamber involves the shape of the combustion chamber, the location of spark plug, and also the location of inlet and exhaust valves. The three main requirements of SI engine chamber are high power output with minimum octane requirement, high thermal efficiency, and smooth engine operation. Now, higher power output requires high compression ratio, small or no excess air, no dead pockets, optimum degree of turbulence, high volumetric efficiency. Whereas high thermal efficiency require high compression ratio, less heat loss during combustion, and a proper scavenging of the exhaust gases. Whereas smooth engine operation means moderate rate of pressure rise during compression, means rate of pressure rise should not be high, it should be moderate, neither low. Absence of detonation, which again means that combustion chamber has to be compact, proper location of spark plug and exhaust valve, and satisfactory cooling of the spark plug points. Now, if we say that higher power output is required, then definitely it means we need high compression ratio, or small or no excess air, or complete utilization of air, or the optimum degree of turbulence, or the high volumetric efficiency. Now, we take up one by one. High compression ratio. See, the compression ratio is limited by the phenomena of detonation. As we know that if we increase the compression ratio, efficiency of engine increases. Now, detonation depends on the design of combustion chamber and fuel quality. Any change in design that improves the anti-knock characteristics of combustion chamber permits the use of high compression ratio, which should result in higher output and efficiency. Now, if we are using small amount of excess air, or you can say no excess air, then that can basically result in higher power output. If there are no dead pockets, then definitely it will lead to the complete utilization of the air, and that will enhance the power output of the engine. Now, optimum degree of turbulence. Turbulence is induced by inlet flow configuration, means by the suitable design of inlet manifolds. We can affect or impact the turbulence. A squish is the rapid ejection of the gas trapped between the piston and some flat or corresponding surfaces in the cylinder head. Turbulence induced by squish is preferable to inlet turbulence since the volumetric efficiency is not affected. Now, higher volumetric efficiency. This can be achieved by having large diameter valves with sufficient clearance around the valve heads, proper valve timing, and straight passageways by streamlining the combustion chamber, so that flow is not having any restriction or less restriction is there, so that basically lesser pressure drop results. It means more charge per stroke and proportionate increase in the power output. Large valves and straight ways increase the speed at which the maximum power is obtained, and it increases the power output by increasing the displacement per minute. Now, high thermal efficiency requires high compression ratio. We have discussed about high compression ratio in the previous slide only. Now, small heat loss during combustion is also an important aspect to achieve high thermal efficiency. This can be achieved by having a compact combustion chamber. Now, if we have compact combustion chamber, the other advantage could be reduced flame travel. So with a given turbulence, this further reduces the time of combustion and hence combustion time loss. Good scavenging of the exhaust gases also basically lead us to achieve high thermal efficiency. Now, smooth engine operation means moderate rate of pressure rise during combustion, means free from vibration, jerks, or periodicity of the movements. Absence of detonation, and absence of detonation means again it requires basically compact combustion chamber, means short distance of flame travel from sparking plug to the farthest point in the combustion space. So pockets should be avoided in which stagnant gas may get collect. Those pockets should be avoided in the combustion space. Proper location of spark plug and exhaust plug, so they don't serve as hot spots and lead to the detonation. Satisfactory cooling of the spark plug points should be achieved, so that will basically avoid the pre-ignition. And also sufficient cooling of exhaust valve head is required, because exhaust valve head is basically the hottest region of the combustion chamber. Now the basic requirements of higher power output, high thermal efficiency and smooth engine operation can be achieved by the design principles that we are going to discuss now. Now if we want to achieve high volumetric efficiency, then the combustion chamber should have largest possible inlet valve with sufficient clearance around the valve heads, because that will basically allow the maximum amount of air or charge to enter the cylinder. Now to prevent detonation, the length or the flame travel from the sparking plug to the farthest point in the combustion space, that is farthest point means the end space region, should be as short as possible. Now this affects the location of spark plug, the position of valves and the shape of the combustion chamber. It basically says that bore of the cylinder should be small, because I have said that length of flame travel should be small. So definitely it leads to the conclusion that bore of the cylinder should be small. So SI engine are therefore generally limited up to 100 mm of cylinder. Means you will rarely find any SI engine cylinder which is having bore greater than 100 mm. There is no such limitation on CI engine. Now to reduce the possibility of detonation, there should not be a hot surface in the end gas region. Exhaust valve is a very hot surface, that should therefore it should not be in the end gas region. It means that exhaust valve should be near the spark plug, so as to avoid the surface ignition. As exhaust valve is hot surface, so it should be kept small, and to compensate for its less size, its lift is made higher so that scavenging can take properly. Now short combustion time is the important consideration in all SI combustion chamber designs, and it can be achieved by creating the highest flame front velocity through creation of correct amount of turbulence. Now the requisite turbulence may be created by suitable positioning of the inlet valves. and design of inlet passage, and also the streamlining of the combustion chamber. The shape of combustion chamber should be such that the largest mass of the charge burns as soon as possible after ignition, with progressive reduction in the mass of charge burned towards the end of combustion. To ensure high thermal efficiency and satisfactory initial combustion condition, the heat flow should be minimum in the zone around spark plug. Now, for minimum heat flow, the surface volume ratio should be least. And this is basically provided by the hemispherical shape. Moreover, a lower surface volume ratio also leads to less air pollution. In the end gas region, surface volume ratio should be large so that there is good cooling in detonation zone. In order to able to extend the mixture range as far as possible on the weak side and more especially on reduced load, it is important that spark plug should be positioned so that there is no skewing of any residual exhaust products by the incoming charge. The exhaust valve head needs to be cooled sufficiently with the help of high velocity water stream around it, because it is the hottest spot of the combustion chamber. There should be sufficient cooling of the spark plug points by high velocity water stream in order to prevent pre-ignition at the large throttle openings. There should be good scavenging of the exhaust gases. Uniform thickness of walls for uniform expansion also prevents the chances of detonation. Highest possible compression ratio to achieve maximum thermal efficiency and prevent detonation or rough running at all running conditions is the most important requisite condition in order to prevent detonation. Now we'll take up the historical review of combustion chamber design so that we can come to know that what improvements were made progressively throughout the journey of the development of combustion chamber designs. Now this is basically the T-head type combustion chamber, and it was one of the earliest design. The T-head design had the disadvantage of having two camshafts. Now it was also prone to detonation. The reason being the distance across the combustion chamber was too long. So there was violent detonation even at the lower compression ratio of 4. The another factor was that at that time, means this is the time of the first decade of the 20th century, that is around about 1908. So at that time, the average octane number of the petrol available was that 45 to 50. So when the octane number available was low, so it also basically restricted the use of higher compression ratio than the compression ratio of 4. So chronologically, the sidewall combustion chamber followed the T-head combustion chamber, and it was very popular for the petrol engines in the period of 1910 to 1930. The chief feature of this sidewall combustion chamber was that walls were placed side by side and were in the same engine block. Now this offered the advantage from both manufacturing point of view as well as maintenance point of view, as it was easy to enclose and lubricate the valve mechanism, and moreover the detachable head could be removed for decarbonizing without disturbing either the valve gear or the main pipe work. Now it also gave poor performance because of following defects like lack of turbulence, as the air had to take 2 right-angle turns to enter the cylinder, and in doing so it lost much of its kinetic energy. Moreover, extremely prone to detonation due to large flame length and slow combustion process due to lack of turbulence. And it was extremely sensitive to ignition timing due to slow combustion process. So because of all these defects, sidewall combustion chamber design could not use high compression ratio as the contemporary overhead valve engines could do, and could not compare with them in power or economy. Chronologically, this overhead valve or I-head combustion chamber followed T combustion chamber design, and it was popular about 1950 or so. The main feature of this combustion chamber was that both the valves were located in the head, and this overhead valve engine design basically superseded the side valve combustion chamber design because it could be employed for higher compression ratio, and there were basically certain reasons behind that, which we are going to discuss just now. Now in this I-head combustion chamber or overhead valve combustion chamber, the pumping losses were lower and the volumetric efficiency was higher because of enhanced intake of the engine, intake of the charge or intake of the air fuel mixture, you can say, because valve size were larger, or you can say valve lifts were higher, and also there were direct passageways. So all these factors led to the enhanced breathing of the charge in these cylinders, in these combustion chamber designs. Moreover, the less distance which was there in the case of overhead valve chamber design for the flame to travel basically eliminated, or you can say minimized, knock up to a great extent, and therefore it led to the requirement of fuel which could have lower octane number. Another thing was that less force was subjected on the head bolts, and because of that there was less possibility of leakage of compression gases or jacket water. The projected area of a side valve combustion chamber is inevitably greater than that of overhead valve chamber. Now, the removal of hot exhaust valve from the block to the head confined heat failures to the head. So the absence of exhaust valve from block also resulted in more uniform cooling of cylinder and piston. Now here S by V ratio was lower, so therefore heat loss was also lower and air pollution was also lower. It was easier to cast this configuration, means it was easier to design, or it was easy to manufacture the overhead valve or I-head combustion chamber rather than the previous one. So Basically, it led to the lower casting cost. So now we want to discuss about F-head combustion chamber. Basically, F-head combustion chamber are the combustion chambers in which one valve is in head and the other is in cylinder block. And this design is basically a compromise between side valve combustion chamber and overhead valve combustion chamber. Now, if we talk especially about the rower design which we have shown on the slide, then basically it has a piston with shaped crown and a sloping cylinder head. The inlet and exhaust valve are also inclined. You can see in the figure. The plug is in a good position in the flat roof of the chamber. Basically, because of the flat roof, one can use a bigger inlet valve. Means inlet valve is bigger than exhaust valve, and this is basically facilitated by flat roof. The cooling of the valve, that is exhaust valve and spark plug, that is efficient. The effective flame travel is short and the end gas is reduced to a thin layer bounded by relatively cool piston and inlet valve. So basically all these factors lead to a good resistance to detonation. So basically this design is a perfect one and it is possessing all the requisite requirements for a good combustion chamber, that is high volumetric efficiency, maximum compression ratio, for a fuel of given octane rating, and high thermal efficiency. This can operate on leaner air fuel ratios also, and that too without misfiring. The only drawback, the main drawback of this design is that basically the mechanism is quite complex for the operation of valves, and the piston is also of a special shape and size. So this is all for this lecture, in which we covered the abnormal combustion in SI engines and the design principles of combustion chamber in SI engine.